some result on the random band matrix, but this work is related to some conjecture on band matrix, and this conjecture is related to some important conjectures in other fields. So as you can see, there are three big fields: random Schrödinger operators, random band matrices, and quantum chaos. First, let's look at this. Wait a second. Let's look at this relative easy model, just this Schrödinger operators. Here, I look at this operator, this H. This operator is on the L2 ZD, Z just the integers, the d-dimensional integer letters, L2 space. This operator, this delta is just the regular Laplacian operator. And this V is a multiplication operator. So the definition is like this. If you have a Psi, which is in L2 ZD, then the delta phi is defined as this just the neighbors minus it and the sum of the neighbors. This is standard Laplacian operator. And this V is multiplication, just the x component of V Psi equals to Vx times Psi x. For this is the regular Schrödinger operator. This is just two parts, Laplacian and this V. Later I will discuss this, the why we writing this way. In the random Schrödinger equation, this V usually is random. For this V, usually this Vx is ID. Random variables could be one or a positive one or negative one, a probability half-half. This is the regular case. I'll say my mistake. Okay. So it looks like a very simple operator, just two components, right? It's the Laplacian and this V. But if you look closer about the eigenvectors of these two components, we find out they're quite different. They look similar. This is the neighbors. This is just the Vx. But if you look at the eigenvectors, you find out for this Laplacian operator, the eigenvector, maybe I should not call it eigenvector, but roughly just that we have this relation, this delta on this phi k is lambda k times phi k if this phi k is a wave function, e to the k dot xi. For this wave function, of course, this eigenvector is extended. It's everywhere, roughly speaking, it's everywhere. But if you look at this V is quite different. This V is multiplication. Just you have a Psi, then this the V Psi is just the V times Psi, right? So you find out the eigenvector of this one, of this V, is just a delta function. For any delta function, just this phi, delta function is the eigenvector of this V. So for these two operators, we find out all of the eigenvectors of this operator is extended, it's everywhere. And all eigenvectors of this operator is delta function. We call it localized, we call it really localized. It's not simple because it's only supported on one point. So it's a very natural question to ask. How about the H? H is the minus delta plus V. This in physics, this is kinetic energy, this is potential energy, and this is Hamiltonian. This is not important, but for us, we want to know if we have this operator, we have this matrix. This matrix is multiplication. It's like you multiply a diagonal matrix. This matrix is it's just a narrow matrix. How about the eigenvector of this H? In physics, for physics, this is a very important question because if the eigenvectors are extended, then which means this system is a conductor system. And if this eigenvector of this one is localized, then it means this system, this physics system, this is insulated. So what is the answer for this one? Just now, this one is totally extended. This one is totally diagonal. It turns out the answer is not that trivial. The answer is the Anderson conjecture. Anderson conjecture says if you have this H, this kinetic energy plus the potential energy, you have this lambda. Lambda is a constant. Sorry, I can hear someone speaking. Maybe not important. The V, let's say just half. Let's say V is, or maybe Gaussian mean zero, variance 1. For in Anderson's conjecture, it says for D is the dimension, 1 dimension or 2 dimension. If D equals to 1 or 2, no matter how small this lambda is, the spectrum is points. We don't discuss spectrum at here. Let's just look at eigenvectors are localized. Interesting. The eigenvector for this one is not, it's extended. The eigenvector for this one is localized, but doesn't matter how small this lambda is, the eigenvector of this H is localized. Actually, it's localized, but doesn't mean it's a delta function. It's just mean it's not extended to everywhere. It's like a bump. It's like here. That's just and here in this conjecture they have this localization length of this function. First let's look at this example. Just say if I have a function which is this one, this function fx equals to this, then for this function I would say the localization length is about lambda, because if you look at this fx, look at absolute value of fx, it looks like a bump, and the width is about lambda. So this is about lambda, like I said. So in this conjecture, it says this. In this conjecture, it says then the local length for d equals to 1 is this large, and for d equals to 2, it should be this large. But one thing I try to find out is whether there are some numerical results on this one, on d equal to 2 case. Actually, I did not find out. It seems very hard to do this numerical calculation, because you see that when lambda is small, this is e to the lambda to the -2. So this could be a very large number. So maybe that's the reason I did not find out any numerical results on this one. The reason people believe this is correct is based on some non-rigorous supersymmetric methods. And when d equal to 3, this is interesting. D equal to 3, people find out that actually the threshold, if the lambda is small, when lambda is small, then this eigenvector is extended. It's everywhere. When lambda is large than this lambda c, this threshold, then you will have some localization length. Now, this is the conjecture. Actually, for this one, I also did not find out any numerical results. For this one, for d equal to 1, there's some numerical result, but for this one, I think no conjecture on what is this lambda c, even for the simple v case. So this is the Anderson conjecture. It says, oh, let's see, this is 2. You can think about this operator because it's linear operator, so you can consider this a matrix. So this is a diagonal matrix. This looks a narrow matrix, and put them together, you find out we have this conjectures. People had worked on this conjecture for a very, very long time. Now let's come back to our random matrix. Random band matrix is similar to the question. you have seen in the random Schrodinger operator. But here we really talk about the matrix. So as a matrix, again, we talk about this. It's a matrix. You have x and y. X and y are in ZD, but instead of the whole space, we talk about a large box in ZD with the periodic boundary condition. The L is the size of this box. So there's a matrix. For this matrix, the matrix will look like this. This is the L. This is the length is the L. And for this matrix, most entries are zeros. Only when the entries are very close to the diagonal line, then it's non-zero. So let's look at the definition. Definition says this. So we have a matrix. The entries means zero, and the entries are independent to each other up to the symmetry. It's like the Wigner matrix, but the difference is for Wigner matrix, most of them are not zero. The entries are comparable to each other. But at here, only when it's zero if x minus y is larger than w. Only when the x minus y is less or equal to w, this is non-zero. So only when in a very small area, this matrix the entries are non-zero. About this w is much less than this L. In most cases, it's L to the A. This A could be 0.1, 0.2. W is much smaller than L. So this is really a narrow band matrix. That's why we call it band matrix, and we call it random because the entries are IDs. And for this band matrix, we have the similar question. This similar question is this. So if this W is really zero, just only when x equal to y, this is non-zero. If it's really a very narrow one, just diagonal one. If this matrix is really diagonal matrix, then we know the eigenvectors, because the eigenvector can only have one non-zero entries, right? If it's a diagonal matrix, then think about the eigenvectors of this diagonal matrix. We know it's just the standard basis, just the EK or something like that. Oh, okay. So if it's diagonal matrix, then there's only one non-zero entries. And on the other hand, about 10 years ago, the people had already proved for Wigner matrix, the eigenvectors are extended to say most of entries are non-zero entries. So for a full matrix, the eigenvector is extended. And for diagonal matrix, only one entry is non-zero. So it's very natural to ask this question. How about the regular W? If the bandwidth is W, how about the eigenvectors? Whether this eigenvector should be extended or the eigenvector should be localized with some localization length, right? This is a very natural question. So how about the general W case? This is the picture. One thing I need to explain is just the scale is different. The scale is not very good and too late to change it, but I will explain to you. In this numerical calculation, we choose D equals to 1, just one-dimensional, and L is 2000, which means we talk about 2000 times 2000 matrix. And the bandwidth, there's 3 different cases. This one is W is L to the quarter, this is L to the half, this is L to the 3/4. And we find out in this case, the eigenvector, most eigenvectors are localized. They look like a very strong peak. And for this case, most eigenvectors are delocalized. It's just all of them are small. All of them are just some are big, some are small. There's no peak, just extended eigenvectors. And in the middle, when W is L to the half, then it looks like this. Some of them may be large, some of them may be small. This is something in the middle. So on the left-hand side is when W is small, compared with L, you will see the peak. And when on the right-hand side is if W is big, then you will see the extended eigenvectors. So one thing later I will mention is actually one key result in this talk is it's just that our main result is we recently proved when D is larger than 7, then in most cases it's always the third case. Just when D is larger than 7, as long as W is when D is larger and equal to 7, as long as W is much larger than L to the epsilon, for any epsilon, then the eigenvector will look like this. Just extend it. This actually matches the conjecture I'm going to talk about. What is the conjecture for random band matrix? There is a conjecture. This conjecture says there is a threshold, this the bandwidth. If the box is L, there's a threshold for the localization and delocalization. And the answer is this. The answer is this is based on the numerical results in 90s. This is and some supersymmetric arguments. We have this. Let me explain this. Just say this: when D equal to 1, the threshold is L square root of L, and when D equal to 2, then the threshold is square root of log L. So it's already a very small thing about it. You have L, and as long as W is larger than square root of log L, then the eigenvector will be extended. And for D is larger than 3, then people believe as long as it's larger than some constant, some large constants, like maybe this is 10 or 7, then you will see the eigenvector is extended. Again, I tried very hard to find out the numerical results for D equal to 2 and D equal to D equal to 2 and D is larger and equal to 3, and I did not find out some good enough numerical estimates, numerical results on this. These two conjectures are based on the non-rigorous supersymmetric arguments and some other type of some other non-rigorous arguments. Okay, so which means for band matrix we have a similar results, which is when the band is wide enough, the eigenvector are extended. When band is small enough, then this is localized. And if you compare what I said about Anderson model, you'll find out the things are very interesting. Because previously I said the conjecture on the random band matrix is like this: is D equals to 1. If we fix the W, if we say we fix the band width, but we change the box size, the L, we find out if the L is much larger than the W square. You can just make sure you can see both of my hands in the camera. If you say you fix W, but you change the size of the box, if the box is much larger than W square, by the conjecture, what you can see is the localized eigenvector. And if the L is much smaller than W squared, then you will not see local, you will see delocalized. So it's kind of to say, if you have a band matrix, the band is W, then for the eigenvector, the localization, the localization length of this band matrix will be W squared, because if the box is larger than W squared, then you will see localized. If it's smaller than W squared, you will see delocalized. So when the band is W, the localization length is W squared. This is for the D equal to 1 case. And you compare this with the Anderson model. If we replace, just look at, if we believe this relation, the lambda in the Anderson model compared with the W in the band matrix model, you find out they actually match. It's very interesting. They actually match. So, so if you look at random band matrix conjecture, it will tell you the localization length for d equal to 1 is W squared, and this is the lambda minus 2. And this is e to the W squared, and the match e to the lambda minus 2. And similarly, when W is large enough, the localization length is infinity, and this match the conjecture in the Anderson model. So it's interesting. It's just, but on the other hand, I can only find out numerical results at this part, but these two are still open. Still, but especially what is the threshold? No, it's not clear about that. Okay, let me quickly check the time. I should stop at, okay, I still have 20 minutes. So it's interesting. These two conjectures are both of them are very big conjectures in two different fields, but people found out they actually match in some sense. Right. So what we proved is this. What we proved is there's the in the last year we published 2 papers, and this year very soon we will upload the third paper on this topic, which we proved is this. Just say if the bandwidth is L to the A, this L is the box size, this bandwidth is L to the A. As long as A is larger than 0 and D is larger than 7, then almost all the eigenvectors are delocalized. It's extended. It's actually quite general because there's you will find out first we don't need the entries to be Gaussian, and we don't have a very strong the matrix could be quite general. You don't have some particular structure of this matrix. It's a general model. It's general profile of the matrix. And this is about eigenvector. And to prove these results, a key middle step, maybe I should not call it the middle step because that's the key result is this one, is this quantum diffusion. Quantum diffusion says this. If you look at the resolvent of this matrix, we can estimate this resolvent. We can, based on our calculation, this resolvent, of course, is still also a matrix. This is a matrix minus Z and inverse. So this is still a matrix. If you look at the entries of this resolvent matrix, it decays based on the distance between X and Y. Decays based on the distance between X and Y. Decays. And as you know, for random matrix, we use the resolvent a lot, and the smaller the error, the imagined part of Z is, the harder to estimate this G. So in this work, we can let this Z to be as small as L to the L to the 5 minus D. We know the macro scale in this question is L to the minus D, right? So it's so if you think D is large, then we're already very close to the micro scale of this question. And this is called the quantum diffusion. Why do we call it quantum diffusion? Because actually, if we calculate the Fourier transform of this one, we'll find out this fits this diffusion form. There is effective diffusion matrix at here. This P is just this moment. This fits this diffusion form. And this actually was predicted before in physics papers. you can this is we found out in Spencer's review book. So we proved the eigenvector delocalized, and we proved the resultant decays like this, really decays like this. And based on that, based on these two results, we have results byproducts on the universality of this band matrix. Of course, this is not very strong because usually the universality is the hardest part to prove. But at least we showed if D is really large, and the W is larger than this, then for any k points correlation function of the eigenvalues of H converge to the GOE in the following. Sorry, let me say that again. So what we prove is just if you look at fixed k eigenvalues of this band matrix, it should be the same as the k point eigenvalue correlation function of the GOEs. This is the universality result. But of course, this work is weaker, looks weaker than the previous one. This D should be large. The previous one for the eigenvector, we only need D is larger than 7. Again, let me remind you, for the conjecture says as long as D is larger than 3, and this is okay. So so actually this fits the conjecture, because the conjecture says for this band matrix, if the band is larger than the threshold, then what you will see is delocalization and universality. If it's less than the threshold, then what you will see is localization plus the Poisson distribution. So at least this fits the older conjecture. And in our paper, one of the new important methods. In this talk, I'm not going to talk about the proof, but I only want to talk about one thing, just one key word about our proof. In our work, we calculate resolvent as many resolvent, many works on resolvent expansion. People just do the expansion on resolvent. I could explain it. This is kind of like the Feynman diagram expansion in physics in the quantum field theory. Just you do the expansion, you get more and more graphs. We know there in quantum field theory, you need to do some renormalizations. You have this bare electron and naked math, some physics quantities and the renormalization quantities. We are going to do the same thing here. So the main reason we can expand the resolvent to any finite order is we can do some renormalization called spontaneous renormalization. What we can prove is we can prove when you do the expansion again to get more and more graphs, there is a way to organize all these graphs, and you will see some certain terms will cancel in some certain sense. They will not. They don't really cancel. If they really cancel, then the question will be much easier. They don't really cancel, but they will cancel in some sense. This is something we call renormalization, and it's spontaneous renormalization because you don't need to add some extra terms to see the cancellation. They cancel each other. Okay, it's just the keywords. If you here, I just want to introduce these keywords. The details I leave it to read our papers. But it's a long paper. It's these 3 papers, put them together, they are more than 200 pages. Okay. Okay. Oh yes, 10 minutes. Good. Let me quickly talk about another interesting topics here. And this is related to the quantum chaos. The quantum chaos says something like this. Here, let's think about they are the billiards. This is the white part is the table. The black part is the is not the table. Just the white. You put a ball, you hit the ball, you see you checked how the ball goes. You found this is circle, this is ellipse, this is square with a hole. It's called Sinai table. This is like looks like a stadium. You find out if you hit a ball. In these two cases, they look like this. You can see the pattern. It's a very beautiful pattern. But if you hit the ball in these two cases, they are ugly. So this actually the difference between integrable case and chaos case. This is the pattern is very clear. This is everywhere. And people find out one thing very interesting. Just if you look at the energy levels in different billiards, just look at this one. This V is just the boundary the boundary condition. Look at the energy. People find out for the Sinai billiard. Sinai is just this one. If you look at the eigenvalue, the gaps of the eigenvalues, just if you look at the gaps of the eigenvalues, they look like this. They look like the red one. The red one fits what? The red one fits the eigenvalue gaps of some random matrix models. This is Gaussian or orthogonal ensembles. This fits some random matrix models instead of these Poisson models. But if you look at this picture for the circle case, for this integrable case, they fit the Poisson. So chaos case fits the random matrix. Integrable case fits the Poisson case. And then this is the conjecture that just say if the billiards is integrable, then the eigenvalue gaps spacing the gaps between the eigenvalues, the distance between the eigenvalues fits the Poisson. Otherwise, it fits the GOE. But if you look closer, you find out one thing very interesting. This is the integrable case. Integral case, if you look at eigenvector of the integral case, they look like this. They look very beautiful. They have the pattern. The pattern kind of means the eigenvector, the support of the eigenvector localized on some certain sites, not everywhere. So this is kind of like a generalized localization. This is not a peak, but they localized in some certain area. But this one is opposite. This one is definitely not localized. This is delocalized. This is everywhere. So if you compare with the random matrix model, you find out in random matrix model, what people believed is if the eigenvector is localized, then the eigenvector, sorry, let me say that again. So if the eigenvector is localized, then the eigenvalue is Poisson. If it's delocalized, then the eigenvalue is like GOE. And the same at here. If the integrable, then the eigenvector is delocalized, is localized, and the eigenvalue fits the Poisson. If for the chaos case, the eigenvector is delocalized, then the eigenvalue fits the GOE. So again, they match. So it's a big picture about these three topics. So for quantum chaos, for random band matrix, and for Anderson's model, for all of them, we found out they share some similar property, which are when the eigenvectors are localized, the eigenvalue spacing statistics are Poisson. And when the eigenvectors are delocalized, the eigenvalue spacing statistics are a GOE. But as you can guess, this conjecture is, for this conjecture, I did not find out the calculation for d equal to 2 or d equal to 3 case. And this is the for quantum chaos, just if it's instead of disk, it's a ball and something like. It's hard to do this simulation for d equal to 2 or higher case. But the topic is very interesting, right? It's the if I let this 3 case, and they shared something similar. Okay, so I think I need to use the last few minutes to talk about the previous, to quickly say something about the previous results on this topic. Let me just focus on the random matrix. For the random matrix, as I mentioned, when d equals to 1, the conjecture is the threshold is L to the square root of L. And here, sorry, I forgot to change the N to L. It should be L here. Everything should be L, not L. So when d equal to 1, several years ago, with Bohigas, and Yang, we proved if W is much larger than L to the 3/4, then the eigenvectors are delocalized, and we have the bulk universality, and there's something stronger than that, which is called the quantum unique ergodic theorem. Yeah. So this is one direction for d equals to 1, the delocalization case. On the other hand, how about the localization case? For the localization case, the result, so far the results are focused on the Gaussian case, just the entries are Gaussian. Gaussian case starts with Schenker's results, and when W is much less than L, all the N should be L here. Sometimes we use L, sometimes we use N. So when it's less than L to the 1/8, then the eigenvector are localized, and then they improve it to a 1/7. Literally, yesterday, I know this results literally yesterday, and just they have this new results. This new result says for this W, the Gaussian W kind of block matrix, they can reduce this bound. They can improve this bound to L to the 1/4. Again, the thresholds, in this conjecture, the threshold is L square root of L to the half. So delocalization parts has been reduced to a 3/4, and localization parts has been improved to a 1/4, but still a gap in the middle. But for the Poisson eigenvalue statistics, we still don't know. So this is d equals to 1. For d equals to 1, actually for the edge, Soding has very good results. It says when W is larger than L to the 5/6, it should be Tracy-Widom. If it's less than this, it should be Poisson. Again, this is d equals to 1. There's a special case. People can use the supersymmetric methods to have a very clear study. Just when the variance of the entries just equal to this, people can use the symmetric methods, and actually right now they have already proved if W is much larger than L to the square, then the eigenvectors are Gaussian. This is okay. This is d equals to 1. For d equals to 2, or higher. There are some previous results. Here, I'm not going to talk about the details. Just you can see it grows very slowly. As it starts from this, then getting better. But now we can prove we are at for any a is larger than 0, and the d is larger than and equal to 7. We know the eigenvectors are delocalized. But of course, the conjecture is d is larger than equal to 3. Actually, the conjecture is says not just polynomial. Actually, as long as w is much larger than some fixed number, you will see the delocalization. But on the other hand, there's no numerical results to support this conjecture. But again, this is a big goal. I hope someone can prove it in the next few years. Okay, so this is the history. There's only one thing I want to say about this proof. Actually, the details are not important. There's only one thing I want to say about this proof. If you have interest to take a look at our proof, what we did is the resolvent expansion. We have a resolvent, then we do the expansion. There are many other terms, but we do the expansion. We do the expansion. This is getting more and more graphs, and we need to calculate the nth order expansion. What is this n? This n is like the 1 over a. 1 over a. This a is w to the l to the a. This n is 1 over a. So if a is small, you need to do, if a is, let's say, 1%, then n should be 100. So when you need to do the expansion to the nth expansion, and the number of the graphs in our calculation is at least this large. So as you can guess, there's no way to really find out all these graphs. But one thing very important is we want to see the graphs cancel each other. It's not just say you produce a lot of graphs, then say, okay, they're the graphs, then you do the calculation. No, it doesn't work like this. We really need to see the renormalization. We really need to see the spontaneous renormalization, see the cancellation of this, some cancellation of these graphs. This is very important in this proof. So we find a very special way to do that. But on the other hand, if you have interest to read our proof and you have interest to see these graphs, maybe you can find an easier way to see the cancellation of these graphs. I tried by myself to look at these graphs. So when n equals to 4, I think 2 years ago, in one summer, I spent 2 months to do the coding. And I wrote 10,000 lines of codes with the math lab. And then I run the computer, and after 1 week, the computer is still working, but I did not see any result come out. So I gave up. I think, okay, let's just prove it with math instead of just check the graphs. So if you have interests, you may think about, maybe you will find an easier way to cancel these graphs, because cancel the graphs is the key of this proof. Okay, that's what I'm going to say about this, the proof part.